That scatter plot looks fairly linear, and if you were going to put in a best fit line, it's pretty clear where it would go. The real name for such a best fit line is a regression line. Like it says there, a regression line is a straight line that fits the data in the scatter plot the best. The general form for the equation of a regression line is in that next box. The key thing that a lot of people forget is the hat over the y. Notationally, y by itself means observed y value, and y hat, like it is there, means predicted y value. And that's what you get from the equation of a regression line. You get predicted y values, not observed y values. Other than that, the number multiplied by x would be the slope, and the standalone constant term would be the intercept. Maybe those placeholders are a little bit different than what you see in algebra, where a lot of times in algebra it's y equals mx plus b, so m stands for the slope and b stands for the intercept. Here it's slightly different, but it's still the number multiplied by x is your slope, and the standalone constant is your intercept. Here's the equation of the regression line for the scatter plot that shows up at the beginning of the section 2.6 notes. You can either write the equation of the regression line with x and y, or you can write it with abbreviated terminology for the two variables. Either y hat equals 37.7 plus 0.23 times x, or predicted temperature equals 37.7 plus 0.23 times the number of chirps per minute. One of the main functions of the regression line is to use it for prediction. That ends up being relatively simple if you already have the equation of the regression line. You substitute in a specified value for x, and then you simplify it, and that'll give you your predicted y value. Like it says there, if the number of cricket chirps per minute is 140, your best guess at the outside temperature, it's what you get when you substitute 140 in for x in the equation of the regression line. Simplifying that, you get 69.9 degrees Fahrenheit for a predicted temperature. There's another predicted temperature. Now if the cricket chirps per minute is 103, the predicted temperature is 61.39 degrees Fahrenheit. So a natural question, since we had a data point in the original sample with 103 chirps per minute, how close was that prediction? It was 63.5 degrees Fahrenheit in the original sample. Here the predicted value is 61.39, so it's off by a couple of degrees. For the example immediately preceding this, y, the observed response value is 63.5. The predicted response value is the one that you get from the regression model. So it's what you get and you substitute in for x and simplify. Here, y hat, the predicted response value is 61.39. The best fit line is the one that on aggregate makes the predicted y values closest to the actual y values. For any data point, the residual or error is computed like it is there, where it's the observed y value minus the predicted y value, always in that order. If there's a consistent order of subtraction, the sign means something, and that's the accepted order of subtraction, observed y minus predicted y. The notation, that second box, that's not in our textbook, but that is the conventional notation to use E for error. You can't use R for residual because R is already being used symbolically to represent the correlation. For the temperature and chirps example residual, we had 63.5 for the observed y, 61.39 for the predicted y, so we get a residual of positive 2.11 degrees Fahrenheit. Since the residuals are computed in the order of observed y minus predicted y, a positive residual indicates that a point is above the regression line, and a negative residual indicates that a point is below the regression line. If a residual is close to 0, that means that the predicted y value and observed y value are close together. If the residual is not close to 0, that means that the observed y value and the predicted y value are far apart. As far as the predictions go, you'd want to see more small residuals, more residuals close to 0 for the predictions from that model to be more trustworthy. The last thing on this slide, for any data set, the residuals add up to 0. So there's nothing wrong with getting a negative residual. Every data set that you have is going to have at least one. The least squares line and the regression line for our purposes are the same thing. Like it says there, the least squares line minimizes the sum of the squared residuals. That's just a more specific way of saying that the least squares line is going to, on aggregate, minimize the distance between the observed y values and predicted y values. Unlike correlation, order does matter as far as the regression model is concerned. So it does matter which variable is the response variable and which variable is the explanatory variable. You can see it here. The one that's written in black was the one that we've been dealing with where we were predicting temperature from the number of chirps per minute. If you reverse the variables, so then you're predicting the number of chirps per minute from temperature, what you get for the slope and intercept are a whole lot different. Interpreting the slope and intercept. There are a few different ways of thinking about the slope in a mathematical sense, like change in y over change in x, rise over run, those sorts of things. But the best way of thinking about the slope for regression is the way that it's written here. The predicted change in y when x increases by 1 unit. Whatever value you have for the slope, essentially what that's telling you is that if x goes up by 1, this is what y hat does. And then there's the interpretation of the intercept, which looks a whole lot like the way that you'd think about a y-intercept in algebra. It's the predicted y value when x equals 0. Usually in algebra, it's just the y value when x equals 0, but a regression model will give you predicted y values, not actual y values. Here are the interpretations for the slope and intercept for the temperature and cricket chirps example. For the slope, if the number of chirps per minute increases by 1, the predicted temperature increases by 0.23 degrees Fahrenheit. There are really 4 things that you have to get in here. X increasing by 1, the y variable increasing by 0.23, the context, and then the fact that it's a predicted y value, not an actual y value. Interpreting the intercept down below, if the number of chirps per minute is 0, the predicted temperature is 37.7 degrees Fahrenheit. I suppose there, if you took the context out, it would be if x equals 0, y hat equals 37.7. But what you want to have would be something like what's there. Again, there are 4 things that you have to have. You have to have x equals 0. You have to have the value for the y-intercept. You have to have that it's a predicted y value. And you have to have the context. Those are the things that need to be in there for the interpretation of the intercept. This is not covered in Chapter 2, but I think this fits into Chapter 2 a whole lot better than it fits into Chapter 7, or Chapter 9, I suppose, if you're using the hardcover version of the book. R squared, formerly called the coefficient of determination, but usually just called R squared, is the proportion or percentage of variation of the y variable accounted for or explained by the linear relationship with the x variable. There are a couple of ways that you can write it out. R squared of the variability in y, whatever your y variable is accounted for by variation in x, whatever your x variable is. Or the one on the bottom, R squared of the variability in y is explained by the linear regression model. Usually the R squared is written as a percentage rather than a proportion, which doesn't matter too much, but that is the convention there. The way that you compute it is fairly literal. You take R, the correlation, and square it. I don't know why the general convention is to capitalize the R and R squared, but have it be lowercase with the correlation. If you wanted them both to be lowercase, I think that's fine. If you wanted them both to be uppercase, I think that's fine. Like it says there, a larger R squared is preferable to a smaller one, but whether a model has a good R squared or a bad R squared is entirely context dependent. There are situations where an R squared of 90% is low, and there are situations where an R squared of 30% is extremely high. It's very, very context dependent. But still, you could compute the R squared to get an idea of how well one model does compared to comparable models. So for the temperature and cricket chirps example, the correlation is 0.991. To compute R squared, really, you just take the 0.991 and square it, and then the convention would be to convert that into percent form. So 0.991 squared is 0.9821, which is about 98.2%. And then the interpretation, about R squared, 98% of the variability in Y, temperature, is explained by variation in X, the number of chirps per minute. Really, I just took that first general interpretation on the previous slide and stuck 98.2 temperature and chirps per minute in there, which will always work. So would that second general interpretation. Those are the ways that you usually see those written, and those templates are always going to work. The first caution with regression is the idea of extrapolation, where you don't want to use the regression line for prediction for x values that are outside the range of the x values in your original sample, because you don't really know what's going on out there. If you look at these two scatter plots that are there, the first one is the fuel price adjusted to $2,005 over time, and it looks like there's a general increasing trend, but then past 1982, look at what happens. Then you have a downward trend. You have almost the exact opposite thing happening. So this is an extreme example, but this is why extrapolation is dangerous, because you don't really know what's past the end of your data set. So as far as using the equation or the regression line for prediction, you want to just stick to x values that are within the range of the x values in your initial sample. Another caution is that you don't want to apply the idea of linear regression to a scatter plot that's clearly nonlinear, like the one that's here on this slide. That one's obviously curved, and you don't want to fit a linear form to that. To try to make linear regression work, what you could do is do a transformation on one or both variables. If this was a really software-heavy class, we'd be doing it, but that would really be the next step. We already saw this in section 2.5, but it's worth pointing out again. Outliers can be very influential on what the regression line looks like, and if you look at the scatter plot that's here, with the outlier included, that dark red point toward the bottom right, what you're going to get for a regression line is going to have a negative slope. Basically, it's going to cut through that cloud of blue points and go toward that red one in the corner. But if you take the outlier out, you're going to get a line with a positive slope, because then it just has to fit to those blue points. So this is a really drastic example, but it's supposed to underscore that outliers can cause trouble, especially if your data set's not very big to begin with, like this one.